Welcome to this session. In this session, we are going to discuss short answers in third module, Algebraic Structures and Combinatorics. So in this, what are the short answer questions? They are asking, define a cyclic group and a generator, define automorphism, define endomorphism, like that. There are so many short answers questions will be there. Now we are discussing one by one. Now first, what is a cyclic group and what is a generator? So a group G is said to be cyclic if there exists one element G such that every element A of G is an integral power of G. Then we can, the integral power of G means we are going to write any element if you are going to consider from the group G, that can be expressed as G power n, and for n is nothing but some integer. It may be either 1 or 2 or 3, like that, any number. So if you are going to consider any group, if we are going to say the group is a cyclic group, the group is a cyclic group, so it is having one, that means suppose I am going to take G, let us say it is having some elements, all these elements are going to represent as a power of some element, then that group is known as a cyclic group. That group is known as a cyclic group. So the integral power of any value, then the integral power of the element is called the generator of the group. So if G is a generator of a cyclic group, then we say that G generates G, or that G is generated G, and it is denoted by, then we are going to represent like this. Let us go for, I am going to explain by taking one example. I am going to consider W4, comma, and multiplication. And W4 is a set I am taking like this. And now this is a group already we were discussed in the previous sessions. And this is a group. Now we are going to represent each and every element of this group, some integral powers of an element, Let us say I am going to take I. I power 0 is 1. And next I power 2. I power 1 is, I am getting I. I power 2 is minus 1. And I power 3 is minus I. See, once again, I am going to take all the elements of W4, as integral powers of I. Suppose I power 0 is 1, so 1 is represented as I power 0. Next, minus 1. Minus 1 I am going to represent as I square. This is I square. Next, I is nothing but I power 1. So this is I power 1. And minus I, this is nothing but I power 3. So all the elements of the group W4 comma into which is a group, all the elements of W4 as represented as W4, I am going to write it as I power 0, I power 1, I power 2, I power 3. All the elements we are going to represent as the integral powers of I. So we can say that W4 comma into is a cyclic group. And what is the generator here? I is the generator. So I is the generator. So, and we are going to represent this cyclic group as like this, I. So this is the definition of a cyclic group, and of course the generator. Now let us go for two groups are given. One is G and another one is G1. G is a a group under the binary operation star. G1 is a group under the binary operation star 1. Under the binary operation star 1. Then F is a mapping from G1 to G to G1. This is G and this is G1. And F is a mapping from G to G1. And F is called a homomorphism. When we say that F is called a homomorphism, for all A comma B belongs to G, for all A comma B belongs to G, so any A comma B belongs to G if I am going to take, and it is closed, subsequently A star B is also belongs to G. Because it is a group under the binary operation star, so G star G is also belongs to this group, and it is having a image. It is having a image. So that image is nothing but F of A star 1. This is because Z1 is a binary group under the binary operation star 1 and F of B. F of A star 1, F of B. Then we can say that the mapping is homomorphism. Mapping is homomorphism. So here there are two groups will be there. G is a group under the binary operation star, and G1 is also a group under the binary operation star 1. And now if we are going to consider a function F from G to G1 is called homomorphism. For all A comma B belongs to G, F of A star B is equals to F of A star 1 F of B. Now this homomorphism and a function here G and G1 is different. G and G1 are different. So then we are saying it is a homomorphism. Whenever the mapping is defined from the same set, G to G itself or G1 to G1 itself, then we can say that homomorphism is known as endomorphism. A function F from G to G is said to be endomorphism if it is homomorphism. That means in such a case, and here also G to G only, it is going to map only G to G only. Then such homomorphism, we are going to take it as endomorphism. And next, epimorphism. Another definition is epimorphism. A mapping F from G to G1 is said to be epimorphism. First of all, if it is homomorphism, and if it is F is onto. That means each and every element in G1 which is having a pre-image. So then such a mapping is known as a epimorphism. So a function F from G to G1, both are different groups. G to G1 is said to be epimorphism if F is homomorphism and F is onto. Then another one is monomorphism. A function F from G to G1 is said to be monomorphism if F is homomorphism and 1 to 1. If F is a homomorphism and 1 1. F is a homomorphism and 1 1, then that function is known as monomorphism. And next another one is isomorphism. So what is isomorphism? A function F from G to G1 is said to be isomorphism if it is a homomorphism and 1 1 and onto. So then it is known as a isomorphism. So isomorphism, it is satisfying isomorphism which is going to satisfy homomorphism, and next another one is plus, and next ontoness, and next another one is plus 1 to 1. The function is homomorphism onto and 1 1, then that is known as isomorphism, and then we are going to define that as G is isomorphic to G1. So these are a few definitions, completely depends on the homomorphism function concept. All are only the mapping is from G to itself, and if it is homomorphism, then we are going to call it as endomorphism. And F is a mapping from G to G1, and if it is a homomorphism and onto, then it is known as epimorphism. And next F is a mapping from G to G1. If it is homomorphism and one-to-one, then it is a monomorphism. And next F is a mapping from G to G1. If it is a homomorphism, one and onto, then it is known as isomorphism. And next another one is the automorphism, the isomorphic of a group G to itself. So this is F is from G to G dash. G to G dash. Suppose F is from G to G itself and satisfying all the three conditions, then that is known as a automorphism. Then that is known as a automorphism. And the next another definition, kernel of a homomorphism. So homomorphism. F is a mapping from G to G1 is the set of all elements G mapped onto identity element of G1 by F. That is the kernel of F written as ker F, here F. So ker F is equals to A belongs to G and F of A belongs to E1. E1 is the identity element in G1. Identity element in G1. Then that is known as a kernel of homomorphism. Kernel of homomorphism, or simply we are going to write it as a ker F. Ker F is equals to A belongs to G such that F of A is equals to E1 and F of A is nothing but which is the element in G1 and it is mapped to the identity element. Now, we are going to discuss a few more definitions. See here, S is a non-empty set and a star is any binary operation, is an algebraic structure in which S is a non-empty set and a star is a binary operation, and if it is closed under the binary operation star, such a structure consisting of a non-empty set and a binary operation defined on the set S is known as a groupoid. So here that means a binary operation which is closed defined on the set S is known as a groupoid. So here an algebraic structure S comma star is called a semigroup if it is a binary operation is closed and associative. Already we discussed in the question bank problems. And a semigroup is nothing but S comma star is a semigroup. First of all, S is closed under the binary operation star and S satisfies associative property under the binary operation star. Then these two conditions are satisfied. Then we can say that S comma star is a semigroup. Now any semigroup if we are going to consider, and if it is additionally satisfying identity element, then we can say that it is a monoid. So monoid means it is a closed property satisfies and associative property satisfies and identity element satisfies. Then we can say that it is a monoid. And similarly, the group up to here it is a monoid. Then after that it is having every element is having its inverse. Then we can say that G comma star is a group. So it is small a star B. So belongs to G for all A comma B belongs to G, and A star B star C is equals to A star BC for all ABC belongs to G. It is associative identity and every element is having its inverse. Then any binary operation or any non-empty set which is satisfying all the four properties under the binary operation star, then we can say that it is a group. So additionally, for the group, if G is commutative under binary operation, then we can say that it is an abelian group. It is an abelian group. That is AB is equals to BA. AB is equals to BA. So then we can say that G is an abelian group. Now, the group, a group G comma star is said to be a finite group of order n. Finite group of order n if G is a finite set which is having n elements. With the cardinality of G. Cardinality of G is nothing but number of elements in G. Number of elements in G is equals to n. So then we can write the order of G. Order of G is equals to n. So a group G comma star where G is not a finite set. Then is called an infinite group. If G is not a finite set, then it is known as a infinite group. Now, the sum rule. So here, which is a combinatorics, the sum rule. What is a sum rule? Define the sum rule, and we are going to discuss with an example. So here, suppose the two tasks are there, T1 and T2. These two tasks are performed. So it should be performed. If T1 can be performed in m ways and T2 can be performed in n different ways, then if one of these, that means these two tasks cannot be performed simultaneously. Then one of the two tasks, this is important, one of the two tasks can be performed in m plus n ways. So here T1 is one task, T2 is one task. T1 is going to be m1 ways, it is going to be performed, and it is going to be performed in n ways. So we are going to perform either T1 or T2. In how many ways? It is m plus n ways. We are going to perform. So if you are going to generalize this, there are k tasks will be there. T1, T2, T3 and so on, Tk. And these k tasks performed in n1 ways, n2 ways, n3 ways and so on. Each and every T1 is performed in n1 ways and T2 is performed in n2 ways. T2 is performed in n2 ways and T3 is performed in n3 ways and Tk is performed in nk ways. Then any one of these tasks are going to be performed, either T1 or T2 or T3 and so on. Tk is nothing but n1 plus n2 plus n3 and so on plus nk ways. So this is known as a sum rule. Suppose if you are going to consider one example, in how many ways there are 16 boys and 18 girls in a classroom, we wish to select one of the student, either boy or girl, or as a class representative. So how many boys are there? There are 16 boys are there. So how many girls will be there? There are 18 girls will be there. The task is selecting a class representative. Who is a boy is a T1. And selecting a class representative who is a girl, it is task 2. Selecting a class representative may be either boy or girl. So in such a case, we are going to use the sum rule. So how many possible ways to select a boy? 16 possible ways. And to select a girl, 18 possible ways. To select any one of these, just we are going to add m plus n ways. So 16 plus 18, that is nothing but 34 ways we are going to select a representative, select a class representative who is either boy or girl. And now the product rule. Another one is a product rule. Suppose there are two tasks, T1 and T2, performed one after the other. So one task is going to be performed after the other task is also going to be performed. So in the previous sum rule is any one of the tasks is going to be performed. Here product rule is nothing but one after the other tasks should be performed. tasks should be performed. In how many ways? See here, T1 is performed in N1 ways, T2 is performed in N2 ways. So the number of ways that we are going to perform T1 and T2 one after the other is N1 into N2 ways. N1 into N2 ways. And more generally, if you are going to define, there are k tasks will be there. There are k tasks will be there. T1, T2 and so on, Tk. So T1 is going to be performed in N1 ways and so on. Tk is performed in Nk ways. Then one after the other task is going to be performed in N1, N2 into N3 and so on in Nk ways. So we are going to multiply all the number of ways. So here, let us consider one example. Suppose a person is having 3 shirts and 5 ties. So shirt as well as a tie. Wearing a shirt is one task. Wearing a tie is another task. Wearing a tie is another task. So we are going to perform shirt as well as a tie. Shirt as well as a tie. So one after the other we have to perform these 2 tasks. So one is 3 ways and another one is 5 ways. So one after the other, these 2 tasks can be performed in 15 different ways. That is m into n ways. M into n ways. So that is nothing but we are going to use the product. So now let us consider some of the problems in this. Suppose we wish to construct a sequence of 4 symbols in which the first 2 are English letters and the next 2 are single digit letters. First 2 are, see here, we wish to select 4 symbols, 1, 2, 3 and 4. So first 2 are English letters. These 2 are English letters. And the next 2 digits, these 2 are digits. These 2 are digits. Okay, now in if no letter or digit can be repeated, then the number of different sequences that we can construct is, suppose here, this is the first way. How many ways that I am going to allot the English letters? 26 ways. First, to fill the first space, and whatever you are going to fill that, and that letter English alphabet is not going to be used in the second one. So then we are going to use in 25 different ways. 25 different symbols we are going to use. And similarly, this is the numbers. So for this, 10 numbers we are going to use, and that number we are not going to use there. Then it is 9 numbers. So no number, no letter can be repeated. What is the total number of ways is? Then we are going to multiply this. We are going to multiply the total number one after the other. Anyhow, we have to fill all the 4 character sequence. So we have to fill all the sequence. So how many ways? This is nothing but a product rule. So here, first one is a task T1 is assigning first English letter in the first space. And the second task is assign second English letter in the second space. And the third space allocate, and next allocate digit. So allocate the digits, okay, in the third characters. And the fourth task is allocate the digit, so which is not used the earlier in the third digit. That is the fourth task. For this is fourth task. So if I am going to take in this order and I am going to get, that means whatever the English letter that we are going to use, that letter will not be used in the next space. And whatever the digit we are going to use in the third space, that should not be used in fourth one. Suppose that condition is not required. That condition is not required. So first space, how many characters? 26 characters will be there. 26 ways that we are going to fill. And second also there is no constraint. Then second also there will be a 26 ways will be there. And similarly, the third is 10 digits will be there. And the fourth space is also 10 digits will be there. The total number of different ways that we can construct is 26 into 26 into 10 into 10. 10 into 10. So this is the ways that we are going to arrange, the ways that we are going to apply the product rule. Next, the permutation. Suppose that we are given a distinct object and we wish to arrange R of these objects in a line, since there are n ways of choosing the first object, and the second object is n minus ways, and the third object is n2 minus ways, n minus 2 ways, like that if you are going to say, then we are going to arrange one after the other is nothing but NPR. NPR is nothing but n factorial by n minus r factorial. N minus r factorial. Suppose it is required to find the number of permutations that can be formed from a collection of n objects, of which n1 are one type, n2 are the second type, n3 are third type, like that it will be there. The number of permutations of these n objects are n factorial by n1 factorial, n2 factorial, and so on, nk factorial. Suppose let us on this some of the problems which was asked in the previous in the question bank, that we are going to discuss. Now flower. So here how many different strings of length 4 can be performed using the letters of the word flower? So here how many letters will be there? The given word which is having 6 letters are distinct and the required number of permutations are, so 4 length out of 6, so it is nothing but 6p4 ways. So the required number of strings are nothing but 6p4, that is a 360. Suppose here the number of permutations in the word successes. So here there are 7 letters will be there, out of which S is 3 times are repeated, C is 2 times are repeated, and the next remaining is only 1 time. So the required number of permutations are, the total number of letters are 1, 2, 3, 4, 5, 6, 7. 7 factorial by 3 factorial into 2 factorial, because S are repeated 3 times, C are repeated 2 times, and the remaining is repeated 1 time. So we are going to get like this. Now the another one is, how many 9 letters words can be formed by using the letters of the word difficult. So here once again the given word contains 9 letters, out of which there are 2 F's and 2 I's and 1 each of the D, C, U, L, T. That means D will occur only once, C will occur only once, U will occur only once, L will occur once, and T will occur once. Then how many permutations of these we are going to get? So the number of permutations are 9 by, so number of letters are repeated. So F is repeated twice and I is repeated twice, and there is no repetition, the remaining letters. So we are going to get these number of ways. One should arrange the letters which are given in the word difficult. So with this, these are the few short answer questions which are related in the third module, Algebraic Structures and Combinatorics. With this I conclude. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.